Welcome to this biochemistry video on the secondary structure of protein. So as we've noted elsewhere, there are four levels of protein structure. There's primary structure, which is basically the sequence of amino acids. There's secondary structure, which are localized structural elements. Tertiary structure, which is the overall structure of a polypeptide chain, and then there's quaternary structure where we take and link together multiple polypeptide chains or multiple proteins to form some kind of structure. So today we're going to talk about secondary structure. As we mentioned, secondary structure refers to a local spatial arrangement of the polypeptide backbone. There are two very common secondary structures. There's alpha helix and beta sheet, sometimes called beta strand, sometimes called beta pleated strand, sometimes beta pleated sheet. We call them beta sheets and alpha helix, and those are the two primary ones. There's all sorts of turns and loops and other random coils and all other kinds of discussion. We'll briefly introduce some of those today. But, most importantly, you understand alpha helix and beta strands or beta sheets. So the important concept in secondary structure, the one that dictates most of the secondary structure, is the ability of the bonds in the hydrocarbon backbone in this polypeptide chain to rotate. And there are three bonds in there. There's the peptide bond, which you should be familiar with. That's commonly referred to as the omega bond, and that one does not rotate. The other two bonds, the phi and the psi, that exist between the amine and the alpha carbon and the carboxyl, those do rotate, and they rotate freely, and we can actually calculate those, which we'll talk about in a little bit. But those two free rotations give the ability to form localized secondary structure, and you could think about this in terms of they both can, in theory, rotate 180 degrees. And so you can see in the picture here how they could rotate around, and that gives this ability to form localized structure. Now, the R groups can hinder, as you can probably get a picture from this thing, the R groups can hinder this movement, and they influence that movement as well. So those are important concepts all within how free, and so some angles are not realistic based on the size of the R group, and that gives the free rotation some limitations. And two combinations, two R groups next to each other could have real problems just based on their steric hindrance of each other. The important thing we'll show here in a little bit is the Ramachandran plot, which kind of shows where and how secondary structures are favorable, and it also will show where, in particular, alpha helix can form, or different other kinds of helix, as well as beta sheets. That phi and psi bond are really, really important in dictating the secondary structure of a molecule. And while the R groups influence the ability to form these, they are not, as far as sterically, they are not involved in the bond formation that dictates secondary structure. So this kind of gives you an idea of where idealized phi and psi angles are for the different types of structures. So for an alpha helix, it's negative 57 degrees for the phi and negative 47 for the psi, and you could go down the list. This is a great reference and this kind of dictates what a Ramachandran plot's going to tell you. So this is what it's going to look like if your phi and psi angles are at certain locations on this. You're going to get different secondary conformations, and we can determine this using CD, which we'll talk about at the end, and that's CD and FTIR, and this is a CD, which just stands for circular dichroism, and that kind of will tell us where or what secondary structure proteins have. You're going to want to know about Ramachandran plots and how the methods for determining secondary structure. So let's dive in a little bit on the alpha helices. So this these show alpha helices from different angles. So the one on the left shows it from a side view, and you can see that there are about 3.6 residues per turn, and that's about 5.4 angstroms. And what you may note that's really important is we've got hydrogen bonds that are being that are keeping this alpha helix together. But they're only on the hydrocarbon backbone. The R group, you'll notice that there are no bonds that are formed between the R groups on this molecule. So it's absolutely independent of the R group to some extent. There are amino acids that are not favorable in an alpha helix, and there are amino acids that have a propensity to form over others, but generally the R groups do not influence an alpha helix formation. There's most, besides proline and glycine, which are alpha helix breakers, all amino acids generally can form into a alpha helix. Now, proline and glycine can be the start of generally can be a start of an alpha helix, but you're not going to find them generally in an alpha helix. There's always exceptions in biochemistry, but that's a general rule. In the next one, you can see the top view, and you can see how the R groups kind of stick out into space. And there's a very circular rotation about which that this occurs. And same with B, kind of gives you an idea of how all these R groups kind of stick out into space. The top one kind of will give you an idea about the charge, because the helix can also have a dipole type effect where you have a positive on one end and a negative charge on the other end, and that's what you're kind of seeing, and it kind of gives you an idea of how these things are 3.6 turns per rotation. So per rotation, 3.6 residues per rotation in this configuration, an alpha helix configuration. So that's the alpha helix, and it's important. This will be an important thing to note. A couple other side notes on this. The inner diameter of the helix is about 4 to 5 angstroms. Nothing really fits inside there. The outer helix is about 10 to 12 angstroms, and it fits very well into the major group of a double-stranded DNA. And so residues 1 through 8, as you can see also from the figure D, line right up on top of each other. So, and these different groups are these different groups sticking out into space can also influence and put kinks in this if there's some sort of interaction between those R groups at different locations. A 310 helix is a variation of this, of an alpha helix. It's a bit helix as well, much less common. Alpha helix is much more common. So in the right-hand side, you have a canonical alpha helix, and then you have a canonical 310 helix. You can kind of see how the bonds interact a little bit differently. You can also see from the top view that the canonical 310 helix is has a different structure. It has a different organizational shape to it, and so it is found in nature quite prevalently. It's the fourth most common type observed, following beta sheet and reverse turns. You can find it 10 to 15% of all helices in proteins and secondary structures are typically 310 helices. So. And that you could find them sometimes at the end of alpha helices because they can unfold and fold pretty easily. And so some people think that it serves as an intermediate conformation and may initiate alpha helix folding. The 310 helix is a right-handed helical structure, and it does have a very nice 120-degree turn. Basically 3 turns per residue. It's 2 angstroms along the alpha helix and has 10 atoms in the ring, so that form that bond. So it's a very unique structure. I shouldn't say that because it's very unique, and helices are very common, but this is one of the more unique helices that exists. So. This is a pi helix. You can see it's even a little bit different conformation than what the 310 helices. This is also a somewhat common alpha helices unit, and you can kind of just get an idea. I'm not going to go into too much detail on this, but we do know the angles. It has an 87-degree turn. It has 4-point residues per turn, and so we know quite a bit about this, and so we can actually characterize it pretty effectively if we and identify it in proteins. The other most, so those are all the helices that we're going to discuss. Here we're going to talk about beta sheets. Beta sheets come in two flavors. Generally, there's also all kinds of subcategories, but there's parallel and anti-parallel. And basically what you have is, with the turn, with the alpha helices, you have neighbors that interact. Well, here we have direct neighbors that interact in alpha helices. Here we have across the street neighbors, so to speak. They're not the next door neighbor, but they can be a neighboring strand. The beta sheets are also not limited to, you can have beta sheet forms between polypeptide chains, inside polypeptide chains, way down the list or way down the sequence can form. Basically, you end up with this type of structure where the primary amino acid is going, and then you get a turn, and this is an anti-parallel, meaning you can see the direction of the polypeptide chain from amino terminus to carboxy terminus. They're going in different directions, and so you'll notice that the amino acids, this hydrogen bonds that form between the backbone, again, note that this is a backbone bond, backbone functional group bond. Our groups do not interact in this. You'll notice that this is a very straight hydrogen bond, and so it's a little bit stronger than a parallel beta sheet because of the 180-degree orientation of the molecule. These can form more complex structures like barrels and sandwiches, and all kinds of other different structures. We'll talk about those in later when we talk about tertiary structure. The other kind is a parallel beta sheet, and you will note that they're not quite as strong. They are very strong because they have numerous bonds, but you'll notice that they're a little bit at an angle. That decreases the strength of that hydrogen bond, so they're not quite as strong. And they're a little bit more compact than the parallel beta sheet. But you'll notice that they're all in the same orientation. You will see this very commonly when you without turns, because different parts of the molecule interact. We'll also have beta turns in there again, and beta turns occur where strands of beta sheet change directions 180 degrees. This is accomplished in about 4 residues, and commonly glycine is found at these in position 3, because it's a very small molecule, or a very small amino acid that has a lot of ability to rotate freely. Proline is commonly at position 2 because of the kink in proline, and so you usually goes proline, glycine, and then the other amino acids aren't as important. But this beta turn allows for the ability of beta sheets to form more readily. There are other kinds of turns that exist. This is the most common form that exists. We can also have loops or coils, hairpin loops, like you see in DNA. You can have omega loops, you can have extended loops. So like a hairpin loop, an omega loop has 6 to 16 residues, and extended loop is more than 16 residues. But basically you end up with some kind of looping or coil type effects. And you'll see these in things like antibodies, where you have a loop structure that interfaces, or a binding site where these loop kind of stick into a notch or a groove of another protein receptor or something, and those allow for interactions to occur. If I'm going to determine secondary structure, there are 2 methods to do so: circular dichroism, which is based on the polarization of light, and this gives an example of a spectroscopic readout of what a CD would look like, and you can tell from the interactions what sort of secondary structure exists. You also have FTIR, which stands for Fourier transform infrared spectroscopy, which the goal is it's an absorption spectroscopy, and you use Fourier transform to take UV visible or ultraviolet visible light and see at different wavelengths how they absorb. And so both these techniques are used to determine secondary structure of a protein. I look forward to seeing you in the next video.